In the last lecture, we established inequalities on the higher order derivatives of a holomorphic function defined on a domain omega. They were called the Cauchy estimates of the Cauchy inequalities, and we will be using the Cauchy inequalities to establish now that a non-constant holomorphic function defined on the complex plane, it cannot be bounded. Let me write the statement down and we will discuss further. Liouville's theorem states the following. Let f be an entire function. It's defined on the entire complex plane and holomorphic everywhere. Which is bounded. Then f is necessarily a constant function. Then f is a constant function. Let's give a proof of this. The proof, as I have already noted, is going to use Cauchy's inequalities. And in order to do that, let's fix some point z0 in the complex plane and consider, fix a point z0. The first thing to note is that f is a bounded function, and since f is bounded, we can get hold of some m positive such that mod f of z is less than or equal to m for all z in the complex plane. There exists m positive such that mod f of z is less than or equal to m for all z in C. So, in particular, if you consider gamma subscript r, maybe let me use the notation sigma r, the sigma r of t be equal to z0 plus r e to the power it for t in 0 to 2 pi. This is the circle of radius r around z0. Then mod of f of z is less than m, in particular for all z in the image of sigma r for all r positive. This is uniformly actually bounded by capital M. Now, let us bring in the Cauchy estimates to bound the absolute value of f at the point z0. By the Cauchy estimates, f prime of z0 is less than or equal to the supremum of f on the circle of radius m, which is bounded by capital M anyway. So, this is less than or equal to capital M into 1 factorial by r to the power 1, which is r. Notice that the Cauchy inequality told us that fn at z0 is less than or equal to m factorial into m by r to the power n, where m is a bound of f on the circle of radius r around z0. When n is equal to 1 is applied here, we have this estimate. Now, let us take the limit as r goes to infinity. Taking the limit, notice that in general, when we have the Cauchy inequality here, one thing to note here is that this m is actually dependent on r. It is actually the bound on the circle of radius r around z0. So, if you change the circle, the number here will change. But in our case, what is happening is that the m is uniformly bounded by some capital M because f is an entire function which is bounded. So, this is a bound which is uniform on every r, and hence when you take the limit as r goes to infinity, we get f prime of z0 is equal to 0. Because mod f prime of z0 is 0, we have f prime at z0 is equal to 0. And our choice of z0, if you notice, was arbitrary. This implies that f prime is identically equal to 0. Now, by the fundamental theorem of calculus, we have f is a constant function. F is a constant function. So bounded entire functions are necessarily constants. This is actually in stark contrast to what can be seen in the real analysis setting, because if we were to look at the real line and consider functions there, we have functions like sin x, which is differentiable, in fact, which is real analytic, which is bounded by 1. That cannot happen in the complex setting. The moment we have an entire function which is bounded, it's forced to be a constant function. Sin x certainly has an extension to the complex plane, and you should sit down and think about it, that sin z rather, away from the real axis is not bounded. So that's something which we get out of Liouville's theorem. And as an application of Liouville's theorem, let's prove the fundamental theorem of algebra. The classical fundamental theorem of algebra tells us that if you take any non-constant polynomial with coefficients in the complex numbers, then it necessarily splits into linear factors. Let me write it down and let's give a proof of the fundamental theorem of algebra here. This will be a proof through techniques in complex analysis, which makes it more special. Fundamental theorem of algebra. So let P of z be equal to a0 plus a1z plus all the way up to an z to the power n be a non-constant polynomial. That means n is greater than or equal to 1. Polynomial such that an is not equal to 0. Let's think of P to be a polynomial of degree n. Then there exists z1, z2, zn, not necessarily distinct. Let me just note that, not necessarily distinct. Such that P of z is equal to an times z minus z1 all the way up to z minus zn. It splits into linear factors. Oh, notice that this is a polynomial, be a non-constant polynomial with coefficients in the complex numbers, such that, let me just add something here, ai belongs to C and an is not equal to 0. So this is a polynomial with complex coefficients and the leading term is not 0. Then we have our polynomial splits into linear factors. Let's give a proof of the fundamental theorem of algebra. The proof is going to be by induction. Proof is by induction. For n is equal to 0 and n is equal to 0 is not being considered. For n is equal to 1, the theorem is straightforward. Follows directly because it's almost already in the form that we want. It will be something of the type az plus b. You can write it as a times z minus minus of b by a, and that will be our polynomial in the form that we want. Let us assume that the result has been proved for up to n minus 1. Assume that the result has been established up to n minus 1. Now we will prove that the result is true for n as well by a method of contradiction. Let's assume that let P of z equal to a n z to the power n plus up to a0 be a polynomial of degree n That means a n is not equal to 0. Oh, this is not a to the power n, this is a subscript n. I.e. a n is not equal to 0 such that P does not have roots in C, does not have roots. We will show that this will lead to some kind of a contradiction, and hence we will be forced to conclude that P has at least one root in C. Let's see what will happen, what will be the contradiction if P does not have a root in C. The moment P of z is not equal to 0, i.e. P of z is not equal to 0 for all z in C. This implies then 1 by P of z is a polynomial, is actually a holomorphic function. It will not necessarily be a polynomial, but it will certainly be a holomorphic function. It will be in fact an entire function, so it will be holomorphic on the entire complex plane because P does not have any roots, and by the quotient rule you can straightforward one can check that this is going to be a entire function. But then if you notice, if P of z, so if you look at absolute value of P of z, P of z is, what is P of z? It's something of this type, right? If you look at the absolute value of P of z, that is going to be equal to mod of a n z to the power n plus a n minus 1 z to the power n minus 1 all the way up to a0. And by triangle inequality, we can write that this is greater than or equal to mod of a n times z to the power n. So let me write it this way, minus absolute value of a n minus 1 z to the power n minus 1 plus all the way up to a0. And for r, for mod z greater than some capital R, which is say greater than 1, we can say that this is greater than or equal to mod z to the power n times mod a n minus 1 by mod z times absolute value of a n minus 1 plus all the way up to a0 by mod z to the power n minus 1. We can say something like this. Let's now focus on what is written here, or the second term. The second term is 1 by mod z into mod of a n minus 1 plus all the way up to mod a0 by z. There is no mod necessary inside. Here again z minus 1, this is less than or equal to 1 by mod z times mod of a n minus 1 plus all the way up to mod of a0 by mod z to the power n minus 1 by the very simple straightforward triangle inequality. And if we are to pick mod z to be greater than r, which is greater than 1 as well, in particular 1 by mod z will be less than 1, and therefore mod a0 by mod z to the power n minus 1 would be less than mod a0. Similarly, for all other terms, we will be able to write down something like this: mod a0, and by picking mod z as large as we want for r large enough, this is less than or equal to mod a0. By picking mod z to be greater than r, we have 1 by mod z to be less than 1 by r, and by picking r large enough, this can be arranged to be less than or equal to mod a n, sorry, a0 is already there, mod a n. Of course, mod a0 can also be arranged, but we would like to have it less than or equal to mod a n. By rewriting this would just tell us that mod a n minus 1 by mod z times mod a n minus 1 plus all the way up to a0 by z to the power n minus 1, this absolute value. This is greater than, let's arrange for it to be less than 0, and therefore this will be greater than 0. Okay, now let's get back to what we were doing. So this was a slight digression here. This was the digression. We established that for r large enough, this number can be made to be greater than 0. This number rather can be made to be greater than 0. And therefore, so let's say that this is greater than some m prime, which is greater than 0. And therefore, what do we have? We have mod p of z for r large enough. Mod p of z, this is going to be greater than mod z to the power n times m prime, which is greater than r to the power n times m prime. So for again for r large enough, given m positive, there exists r greater than 0, greater than 1, large enough so that mod p of z, this is greater than capital M, and this implies that 1 by mod p of z is less than capital M. All this effort was to establish that outside a disk of closed disk of radius capital R, 1 by mod p of z is bounded. Okay, what can we say about 1 by p of z in the closed disk of radius R? Notice that since our closed disk of radius capital R is compact and 1 by p of z is in particular continuous, and 1 by p of z is continuous, we have 1 by p of z is less than some m1 for all z in D0R bar. And therefore, if you pick m2 to be the maximum of m comma m1, we have 1 by mod p of z is, or rather the absolute value of 1 by p of z, this is less than m2 for all z in C. So that is what we have established just now. But what did Liouville's theorem tell us? Liouville's theorem told us that bounded entire functions cannot be non-constant, and here we have 1 by p of z, which is a entire function which is bounded. So by Liouville's theorem, 1 by p of z is a constant, and that would tell us that p of z is a constant. But that's a contradiction, right? Because p of z is a polynomial of degree n, which is greater than or equal to 1, in fact greater than 1 in the case we are considering, and constant functions have degree 0, which is a contradiction. So our assumption to begin with was false. Hence, there exists at least one root, let's call it Zn in C, such that p of Zn is equal to 0. Now p is a polynomial, in particular it's a holomorphic function, or p is a polynomial, hence we can use factorization directly to p, or if you want to treat it as a holomorphic function, we have also proved that we have a factorization for holomorphic functions. Using that, we will be able to write p of z to be equal to q of z times z minus z times zn, where q of z will be of this type: a n times z to the power n minus 1 plus b n minus 2 times z to the power n minus 2 all the way up to b0. Notice that a n will be preserved because the leading coefficient of p of z is a n. So the a n will be preserved here, and by induction, by the induction hypothesis, q of z is going to be equal to a n times z minus z1 all the way up to z minus Zn minus 1 because it has degree n minus 1, and for all polynomials of degree n minus 1 by induction hypothesis we have assumed that we already have an expression of this type. This implies that p of z is equal to an times z minus z1 into z minus z2 up to z minus zn, and that's precisely what we had set out to prove. We will now prove a form of converse to the Cauchy's theorem. Cauchy's theorem stated that if you have a function which is holomorphic on a given domain omega, and if you have a closed path which is null homotopic, then the integral of f over the closed curve is 0. A form of converse would be to demand that if the integral of f over a closed curve is 0, then our function is holomorphic. So that's going to be the type of statement we will be proving. This theorem is called Moreira's theorem. This is going to be a direct application of the Cauchy integral formula, which is again a consequence of the Cauchy's theorem. Let omega be an open subset of C and f from omega to C be a continuous function. We are not demanding the regularity to be anything more than continuity. So we just start off with a continuous function such that the function f is conservative in the sense that integral of f over gamma, integral of f of z dz. So many times I have been writing just integral of f, but that means integral of f of z dz. This is equal to 0 for all gamma a closed polygonal path in omega. The conclusion is that then f is holomorphic on omega. A moment's thought will tell you that we are not doing much here, because if you go back to the second fundamental theorem of calculus with the added assumption of omega being connected, this ensured that we had an antiderivative which was holomorphic. We will certainly be using that, however, a little more work needs to be done. Let's see. Let's focus on, so even though the notion of holomorphicity has a global nature, the definition is local. So we will focus at some point z0 and at disk where we would like to discuss the holomorphicity. So let z0 be some point in omega and r greater than 0 be such that dz0r is, maybe the bar is contained in omega. And we will focus our attention entirely on dz0r. Any closed curve, any closed polygonal path in dz0r is a closed polygonal path. Let's call the path gamma, polygonal path in omega, and hence integral of f over gamma is equal to 0. But now we are in a good setup. We didn't a priori know whether omega was connected or not. However, the disk of radius r around z0 is certainly connected. In fact, it is much more, but we will only use the fact that it is connected to conclude that by the second fundamental theorem of calculus, because our function f is continuous, there exists a holomorphic function, an antiderivative which is holomorphic. Capital F on dz0 r which is holomorphic. Till now we have not done anything new, we have just used the second fundamental theorem of calculus. But now is where we are going to use the knowledge which we have just gained. Holomorphic functions, because they are complex analytic, we will hence be able to conclude that its derivative is also going to be a holomorphic function. since f is complex analytic, f prime of z. So this is going to satisfy f prime of z is equal to small f of z on dz0r. F prime is a holomorphic function is what we get to conclude on dz0r, i.e. small f is holomorphic on dz0r. Then the choice of z0 was arbitrary, which means that f is holomorphic on omega. So notice that we started off with just a continuous function. The only assumption on the regularity of the function f was that f is a continuous function. And then we used the fact that it will have an antiderivative by the second fundamental theorem of calculus, and because the antiderivative is holomorphic, it's complex analytic, and hence its derivative, the derivatives will also be holomorphic. The derivative will also be holomorphic rather. Moreira's theorem is a standard tool for checking whether a given function is holomorphic or not. Let me give you a direct application of Moreira's theorem to conclude that the uniform limit of holomorphic functions, for example, is going to be holomorphic. Let me just write the statement and see how Moreira's theorem is actually coming into the story. Uniform limit of holomorphic functions. Let's see what this is. Let omega again be an open subset and fn from omega to c be holomorphic on omega for all n in natural numbers, and such that fn's converge uniformly on compact sets, converges uniformly on compact sets to f. Notice that the notion of uniform convergence of fn's to f on compact sets, that's something which can be thought of with respect to the topology on R2 as well. It's the same. It's a topological notion that we are dealing with. The conclusion here will be that then f is also holomorphic. Let's give a quick proof of this. This is going to follow directly from the Cauchy integral formula. Yet again, we have to show that f is holomorphic, which is a local property to be checked, and therefore we will focus our attention in a small neighborhood of our point in question. So let z0 be some point in omega and r positive be such that dz0 r bar is contained in omega. We will focus our attention in this open set dz0 r. So, since fn converges to f uniformly on compact sets in omega, in particular fn's converge to f uniformly on compact sets in dz0r. Now let's take any closed polygonal path in dz0r. Let sigma be a closed polygonal path. In dz0r, in particular, the image of sigma is a compact set, and on the image of sigma, fn converges to f uniformly. Since sigma, let me just abuse notation and say that sigma is compact. What I mean is that the image is compact, fn converges to f uniformly on sigma. And hence the limit, we can now interchange the limit as n goes to infinity of integral of fn over sigma. This is going to be equal to the integral of the limit fn over sigma, which is equal to the integral of f over sigma. But then At each stage, this is 0 by using the Cauchy's theorem, because sigma is a closed polygonal path in a disk of radius r around z0. In particular, any closed path here, this is a convex set simply connected. Every closed path is going to be null homotopic, and by Cauchy's theorem, integral of fn is going to be 0. And this tells us that integral of f over sigma is also equal to 0 for any closed polygonal path in dz0r. By Moreira's theorem now, since f is satisfying the condition that its integral over, oh yes, before I say any of these things, since fn converges to f uniformly on compacts, f is going to be continuous. Since fn's converge to f uniformly on compacts in omega, we have f is continuous. From our theory which we have developed in our real analysis course, f is continuous on omega. So we already have that hypothesis for free. So we can certainly now apply Moreira's theorem to our function to conclude that f is holomorphic on omega. And that's what we were attempting to prove. So before we stop, let's look at, let's summarize rather what are the things that we have concluded about complex valued functions till now on domains in C. If f is a function from say AB into R, where AB is some interval in maybe open AB, that's better, some interval in R, then what do we have about the collection of functions that we have? We have a broad collection of functions which are continuous. F could be continuous, then it will be in this big collection, this big set. If we put more regularity assumptions, then there will be a smaller set which will be differentiable functions. So this, let me call it as, let me not use C1, so I'll just use differentiable. We can actually ensure that for every k there is a function which is k times differentiable and not further. So I'll not write all of them down. Then we have a collection of smooth functions. There are smooth functions, there are differentiable functions, there are k times differentiable functions which are not k plus 1 times differentiable. There are differentiable functions which are not smooth. So this a smooth function is certainly differentiable. So this is a sub collection, and we further have a sub collection of analytic functions. There are smooth functions which are not analytic. Yeah. So for example, e to the power minus 1 by x. Now if you look at functions in an open subset of C, open subset of C, and f be functions on the set omega, we however do not have as many classifications as we have in the real analysis setting. There will certainly be the broad class of continuous functions here, but then the moment we go down to a subclass of complex differentiable functions, complex differentiable on omega, but that is going to be the same as complex analytic functions, in fact. Or rather, let me use the word holomorphic. I should certainly use this. The complex differentiable on omega is just what is captured most times in our course by holomorphic on omega. But this is the same as complex analytic, which we have just proved. These three classes are the same in our case. In fact, so if I had to shade it here, this class is actually the same in our complex analysis setting. Of course, there is one more interesting class of functions which can be put down here. This is the set of all those functions f from omega to c such that integral of f over gamma is equal to 0, where gamma is a closed curve. Now notice that that's actually a special class. If omega, for example, was something like c minus 0, c minus the origin, and if you look at f to be 1 by z, then integral of f over gamma is not necessarily equal to 0. So it's not true that f will always have an antiderivative. Of course, if omega is special, if omega is something like simply connected, then this will also turn out to be the same collection, but that's generally not the case. So there is an extra class here. Of course, we do have an extra collection of functions which can be put here. Those functions which are real differentiable but which are not complex differentiable. Those real differentiable functions which do not satisfy the Cauchy-Riemann equations. Similarly, CK functions for that matter, which do not satisfy the Cauchy-Riemann equations, or smooth functions which do not satisfy the Cauchy-Riemann equations. That's not something which is to be kept apart in our study. They actually do form an integral part of the study, but nevertheless, for the purpose of categorization of complex differentiable functions, we will focus only on them, and this is the diagram capturing that. In the next lecture, we will solve a few problems which will strongly use the various applications and the consequences of Cauchy's theorem that we have discussed in this week.